Good morning, everyone. So I'm Rakshita. I'm a software engineer at Google. And today I'm going to be talking about privacy-enhancing technology that we have built in-house towards provable private insights into Gen AI use. And of course, the work that I'm talking about here describes the work of many, many other folks at Google. So quick agenda before we get started. We'll begin with some motivation, followed by what we exactly mean by provable private insights. Then I'll walk through our system architecture and a real-world application where we've deployed this architecture in production in the Pixel Recorder app. And we'll finally end the talk with some scalability challenges and future work. OK, so let's dive into it. As you all know, we've trained some really, really powerful LLMs on the entire web. But where exactly are we going from here? Well, we've started integrating these LLMs into all our products. And all of us use it on a daily basis. Especially a lot of these on-device Gen AI capabilities are becoming more and more widespread. But these Gen AI features don't really always work the way we hoped they would work. And what do we do in those cases? Well, developers need to have a good way to gather insights into what's working and what's not working, especially for these on-device features using on-device models and on-device data. For example, developers may have questions like, is the user frustrated with this particular Gen AI feature? Or what exact topics is the user talking about? And to add to it, because most of this Gen AI data is largely unstructured, it becomes more of a challenge to gather these meaningful insights. To ground this in a concrete example, let's talk about the Pixel Recorder app for a second. So the Pixel Recorder app provides a lot of Gen AI capabilities, such as summarization of the transcripts, speaker labeling, action item generation, and so on. And a lot of these features use on-device models. And the developers don't really have a good way to identify what are the common failure modes, or even what are the common applications for which some of these capabilities are being used for. And that brings me to this Gen AI development lifecycle. You probably saw this in my colleague's slides yesterday on the talk about Urania. But I wanted to pull this up again to emphasize the importance of learning from user interactions so that we can constantly improve our products and features and develop these AI capabilities. So really what I want to talk about today is how do we gather these meaningful insights, and how do we do it in a privacy-safe manner without compromising user privacy? And that brings me to provable private insights. So what exactly are we trying to do here? OK, we are building a system where unaggregated user data is never visible to humans or the service providers, and only the released outputs is something that the analysts or the developers can eventually see. And even these released outputs come with a formal verifiable privacy guarantee. So when I say private, I'm basically saying that the raw user data should never be visible to humans. The insights here refer to these released outputs that are generated, and the developers and the analysts can look at it and improve their products. And finally, provable here refers to a formal verifiable guarantee where any external third party can look at the system and validate the privacy claims that are being made here. So there are three important pillars to provable private insights. The first pillar is TEAS, or Trusted Execution Environments. So trusted execution environments is basically a secure, isolated area on the main processor, such that any computations that run on the TEAS remain isolated from the rest of the hardware or the rest of the OS. And we'll talk a little bit about the properties that TEAS offer in a bit. But the high-level idea here is that if we run open source code with reproducibly built binaries inside of TEAS, we can actually prove the identity of these privacy-critical components that we're running. The second pillar is the Data Expert LLM, which is basically an LLM that you can run inside the TEAS to gather these meaningful insights from largely unstructured raw data. And the third pillar is differential privacy. So by running differential privacy in TEAS, we can get further formal privacy guarantees. OK, TEAS. There are three important properties I want to talk about today: confidentiality, integrity, and verifiability. So TEAS offer confidentiality by ensuring that all the computations that run on it are protected using hardware-based memory encryption, such that even the root OS or the system operators don't have visibility into what's really running inside of the TEAS, and hence it guarantees confidentiality. It offers integrity by ensuring that the workload that's running inside of the TEAS cannot be tampered with. Again, that provides an isolation barrier from the root OS or the system operator. And it also provides this important property of verifiability, where we can remotely attest and validate exactly what software binary is running on a particular hardware with a cryptographic proof attached to the workload identity. So as I mentioned, T's allow us to prove exactly what specific binary is running on a hardware. And it also helps us create this chain of trust, starting from a client device all the way into the server inside of the T's, so that we can make these bold claims that data from individual devices is never visible to the service provider until it has been anonymously aggregated by the server inside of the T's. And by running these binaries or libraries that do anonymous aggregation inside of T's, and using the property of the T's for remotely attesting exactly what software is running on the T's, we can make these claims. The other two pillars, let's talk a little bit about that. The data expert LLM and DP aggregation. So at a high level, the way this infrastructure works is that there are a few client devices out there that want to upload some data to the server. They encrypt this data and upload it to the server, where it is strictly decrypted only inside of the T's. We then run a data expert LLM on this largely unstructured raw data to gather some meaningful insights. And then we do a private sum over these insights using DP aggregation. And we only release the outputs outside of the T's if certain anonymization guarantees have been met. And by ensuring that all this code inside of the T's is open source and reproducibly built, we improve the trustworthiness of these kind of infrastructures and Google in general. So let's talk about the system architecture. It starts with the client device wanting to upload some minimal set of messages to the server. But before it does that, it talks to this service called as T-hosted KMS, where KMS stands for Key Management Service. And this service itself runs inside of the T's, has open source code, so the client can actually attest exactly what software is running inside of the server before it uses the encryption keys provided by the service. So when the client attests and makes sure that this is the software that's running and it trusts it, it gets those encryption keys, it encrypts its payload using those encryption keys, and then it also ties a data access policy to this encrypted payload before it uploads it to the server. Now, this data access policy dictates exactly what set of processing steps would be run on the server for this particular payload, and only those set of steps are ever run on the server, and no other analysis can be performed on this user's data. So this information is uploaded to the server, it is stored in a storage system in an encrypted form using these keys, and at some later point in time, we run these batch processing pipelines over multiple users' data. These batch processing pipelines, again, run inside of the T's, have open source code. And the important factor here is that the key management service will only share the decryption keys with those particular server-side processing steps, which are already pre-approved by the data access policy. And this ensures that no other server component will ever have access to those decryption keys. And because both the batch processing pipeline as well as the key management service run inside of the T's, the raw data itself remains inaccessible to Google. These batch processing pipelines then run a DP algorithm and finally release an anonymized aggregate to the developer or the analyst, who can then further use it for analysis. Now, the way the verification flow works is that both the key management service and these access policies are endorsed and published to an external transparency log. In this case, we use the Sixtor project or record as our transparency log service. And before the client uploads anything to the server, it basically makes sure that these entries are present in the transparency log. What this gives us is that an external verifier at some later point in time can look at all these entries in the transparency log, and they can retrace back those entries to the actual binary that was run on the server side, and from the binary, they can look up the source code in GitHub to actually inspect the actual code that was run on the user-uploaded data. So all our open source libraries are available at this repository called Google Parfait. It includes our frameworks for simulations, our reference architectures, as well as these components that are run in real Google production deployments. And when we tie this open source code with the capabilities that T's offer, we give the ability to the external verifier to validate exactly what code is run on the user-uploaded data and ensure that that is the only code that will ever be run on that user's uploaded data. This gives a snapshot of our GitHub repository. It basically gives a step-by-step guidance on how you can go from the transparency log entry all the way to the binary, all the way to the GitHub commit, and then all the way to the source code and inspect the code for yourself. So now let's talk about a real-world application where we've deployed this infrastructure in production in the Pixel Recorder app. So in the Pixel Recorder app, we basically use this infrastructure for classifying transcripts, which is largely unstructured raw data, into various categories of interest. It begins with having a transcript that we feed into the LLM extractor in order to categorize it into various categories, such as reminders, business meetings, etc. And then we compute a private sum over these insights using differential privacy. We clip and noise the data, and then release the noised histogram to the analyst. Now, the analyst can decide to tweak this prompt dynamically, and that's totally OK, because our privacy guarantees are on the aggregation algorithm and not on the LLM prompt itself. So even if the analyst were to tweak the prompt in such a way that they wanted to single out a particular user, that would still not be possible because differential privacy would just clip those updates. And because we run all of this inside of the T's, the analyst or Google or any other human does not really have visibility into these raw transcripts. And that provides an additional layer of isolation. This basically shows the results that we were able to obtain by running this example through our infrastructure. So we used an epsilon of 1, and the sizes of these boxes basically denote the frequency of those particular topics. You can read more about it in our published white paper on archive or our blog post. And this basically puts everything together, where we have the Recorder app uploading raw encrypted transcripts to the server, and only the differential private histogram is ultimately released to the developers or analysts. And by ensuring that both the key management service as well as these batch processing pipelines run inside the T's, the raw transcripts themselves remain inaccessible to Google. And because the key management service and these pipelines run open source code with reproducibly built binaries, it provides external third-party verifiers to actually verify the privacy claims that are being made here. Finally, I want to talk about some scalability challenges and the future work. So for this particular example, we used the Gemma 3 4 billion model, and we were able to run processing pipelines for up to 100K inputs. But that said, we are strictly limited because of the speed and memory constraints on CPUs. And so expanding to larger models like the 20 billion Gemma model or large-scale workloads is still a challenge. And so some of the future work that can be explored in this domain would be to use hardware-based accelerators, such as Google TPUs, that is tensor processing units, or GPUs, such as NVIDIA H100s. And by using T's in these hardware-based accelerators, we could basically run more complex models as well as improve the throughput of these pipelines. And finally, that will also help us unlock more richer analysis, such as detailed transcript analysis or private auto-rating, where you can imagine that you can run an LLM inside of the T's and use it for evaluating on-device models with real-world data rather than traditionally used synthetic data. On top of it, you can also explore new capabilities such as DP clustering or Urania that you heard about yesterday. All of this running on this infrastructure inside of T's, providing similar level of verifiability and confidentiality. And this can also be extended to synthetic data generation inside of T's. Thank you for listening.